I'll be presenting on advances in PET image reconstruction. Some of it will be a tutorial for many of you, but that should hopefully ease us in towards the AI and generative AI components. Okay, I need to advance the slide. Is this going to work? Okay, so this is a quick history of where we've come in image reconstruction. So the top left there is good old filtered back projection, effectively a least squares estimator, inverting the radon transform. And then, as you will be aware, we moved on to improve the noise model away from, say, a Gaussian noise model towards a Poisson noise model. And then we had the EM methods, maximum likelihood expectation maximization, giving rise to improvements in image quality, which I hope you can see on this screen. Then we moved on to improving the physics model, for example, improving the positron range model, point spread function modeling, which in turn also gave rise to improvements in image quality. And then, of course, the moment we improve image quality, then what do? We go and reduce the dose, or we shorten the scan time. We end up with poor counts. And so we're going to need to regularize and compensate for the loss of data there. And so that's how we ended up with these map-EM methods. So, for example, a short scan there, 5 minutes. We could regularize that. I'll go into a sort of tutorial on this in a moment, map-EM methods. And then we introduce MR guidance. And that's pretty much where I think we ended up broadly as a field before we entered into the world of AI and deep learning. So let's just quickly review this to try and set the context for the AI methods. This should be very familiar to you, Poisson log likelihood, which is behind that MLEM method, where what we're trying to do is find some image X, which when we forward model with our system matrix gives some model of the mean sinogram data. What we do is compare that to the measured sinogram data. We use the Poisson probability distribution to say what's the probability of getting a certain number of counts M in bin I if the mean was modeled by QI, which of course is modeled by our forward model from our current guess of the image X. And then we define the likelihood, the Poisson likelihood, as considering all of the measured data bins relative to all of the data bins that we've modeled. So this gives us what is the probability of all of those measured counts being those certain values if the mean is given by Q, which indeed is related to our image X. So any image X will deliver a value of the Poisson likelihood. And that's what I'm showing here. That's why I'm writing it in this form to say what is the likelihood of any given image X given some fixed measured data set. And we're just trying to effectively modify X in order to maximize that Poisson likelihood. But that's a rather ugly expression there, and often what we do is use the log of that to simplify things. It won't change the X that maximizes the Poisson likelihood, so we use the Poisson log likelihood. Quite an obvious expression there. And then, of course, as mentioned, we're trying to find the X which will deliver the maximum of that Poisson log likelihood, ignoring that constant term which doesn't affect the location of the maximum. And as you know, we achieve, although no one probably ever has, because I guess we need effectively infinite iterations, we head towards the maximum of that Poisson log likelihood using this non-negative multiplicative updating algorithm called MLEM, which can be loosely related to the gradient, or if you like, the score of the Poisson log likelihood. It does a modification of that gradient of the Poisson log likelihood. Some people can view it as a preconditioner. But in essence, it's just taking us closer to a maximum likelihood estimate in an iterative way. But of course, the problem with maximum likelihood estimation is that we have noisy measured data. So as we go from high count data down to low count data, which could be by reducing the injected activity or shortening the scan time, then what we end up with, if we use MLEM or OSCM, the accelerated version of MLEM, then we end up with significant noise amplification. So therefore, we dealt with the problem of noise, as we all know, over many decades by proposing Bayesian methods or maximum a posteriori methods. First of all, then, just a statement at the top here to say that maximum likelihood estimates are noisy. Noisy data M often gives rise to noisy parameters X, although, of course, they don't have to be noisy. It depends what we choose. It's just that we often choose these tiny little pixels, and so with that choice of parameters, we end up with noisy images. But kernel methods often work around that to avoid such noise. Anyway, let's stick with the map approach, the Bayesian approach, where what we say is let's no longer just work with the likelihood, but now let's have the audacity to claim that we know what the probability of any given particular image X is, and that's our prior probability. This is a probability density function. So we multiply that by the likelihood, and that is proportional to what we call the posterior, which is we're trying to find the X conditioned on the measured data, and that's just given by the likelihood that we've just looked at, multiplied by our prior probability. And it's the prior probability that I'll get into next. Hopefully you've already well understood the Poisson likelihood, but now let's start digging in to what that prior probability might look like that we're multiplying by the likelihood in our expression that we're trying to maximize. We're trying to find the maximum a posteriori estimate. Okay, so often a so-called Gibbs prior is used where we model that probability as being proportional to an exponential of minus beta, that's the hyperparameter controlling the strength of the regularization, beta times some energy function u of x, where what we're saying is any given image x we can associate with some energy value u, so that if an image x has a high energy u, that corresponds to a low probability. Okay, so let's just quickly take a look at some of those examples after I first spell out the map reconstruction objective function, which is the following. We're saying find the x which maximizes not just the Poisson log likelihood, but also is in balance with or takes account of the log of that prior. You remember it was e to the minus beta u of x. Well, when we take the log of it, of course, that exponential disappears, and so we end up with what looks like a penalty for the Poisson log likelihood. And we're now trying to say, let's find the x that maximizes that log posterior density. So looking at that in very simple graphical terms, we could consider the likelihood on the bottom left there. Sorry, I've pressed the wrong button there. Let's see if this works. There we go. So this would be a pixel value x, and typically what we're trying to find is the value of x that would maximize the Poisson log likelihood, but of course that can be noisy. Hence, in comes our prior. If we had a Gaussian prior here corresponding to a quadratic there, then our prior might say, well, actually, the best position is over here, and so the posterior ends up being some compromise, some balance between data fidelity, the Poisson log likelihood, and our prior. So we might have some gradient vector or some direction that's pushing a value x closer towards the maximum of the likelihood. And then we could also have some notion of a direction or a gradient pushing us towards the maximum of the prior. And again, the posterior ends up being some compromised direction to balance those two distributions. Okay, so a quick look at the types of energy function that we might use. This should be very basic revision for most of you, but there's an image that I'm zooming in on. We can look at a pixel value xj, and we can have a go at assessing the energy level of this particular image. First of all, we could, well, it's rather naive just to sum the pixel values, but that is effectively the kind of thing that's being done with a so-called Tikhonov regularization or a quadratic regularizer. You could just naively take the square of all the pixel values, sum it all up, and say if that's large, that's a high energy, and so that's an improbable image. Not very elegant. It's actually better to look at the differences between values and say, okay, we can accommodate large values, but we can't accommodate large differences. So large differences between pixel values would give a high energy. Okay, so that would be like a typical quadratic prior. If we were to take instead the absolute value instead of the square, then that would be total variation. And then one that's already been shown earlier today, the relative difference prior is like a modified version of that where we take into account the overall magnitude of the pixel values that we're looking at the differences between. So we begin to account for the relative difference, if you like, rather than the absolute one. So we don't want to unduly penalize values just because they're large. Right, and as you know, we can also build in some guidance weights there based, for example, on the distance. If they're far apart, then we might want to switch off that penalty term, or if they're close together, then we might want to pay more attention to that penalty term. Okay, and one more key then would be, of course, the use of guidance weights. If we have, for example, a side MR image or some anatomical prior, we can look at the same region of interest, for example, some patch here, and we can look at an MR image for the same region. This is just an illustration here. And we can look at that side image and come up with a similarity map and say, well, if things are similar in this region of the image based on an MR, then in regions that are similar, we will apply this penalty. But if we have dissimilarity, then we can switch off that penalty. And so we have this kind of edge-preserving smoothing of our, or rather we encourage images by having, we don't have such high energy. If there are differences across that boundary, then we don't have a high energy, and so we don't penalize those kinds of images. So it's effectively using MR to guide the regularization. Okay, and if those weights are binary, then that would often be called a Boucher prior. I've shown kind of continuous weights in that bottom left example. Okay, so what does that look like in implementation? Well, this is a very simplified perspective of how you go about doing a reconstruction. We've got our familiar EM update that I've just shown you earlier, but now we have some kind of regularization or denoising update. So we've got two directions to deal with. First of all, we've got the we're dealing with the gradient of the Poisson log likelihood, or I'm going to introduce the notion of the score here just to warm you up for when we get to score-based generative models. So we can view the update as being related to the score of the log likelihood, where the parameter values are the pixel values. And then we've also got an update related to the log of our prior. And so both of these are kind of suggested update steps based on the data on the left-hand side and based on our prior on the right-hand side. And then what we essentially do is merge together those two directions. This is the De Piero method, but also Guabo has come up with a very elegant version of this, and so I think I always look to Guabo's paper when I see that expression on the right-hand side there. But loosely, it's taking us in the direction of higher probability as defined by our quadratic penalty function there, the U of x. Right, so what are the example results of that? So we've got our noisy image on the left side there. And then if we start to introduce our Boucher guidance, so first of all, with no guidance on the left-hand side, we get quite blurred images due to possibly over-regularization. Then as we start to pay attention to that MR guidance information, so we can begin to pick out structures. So that all seems fine, but surely we're going to get a bit concerned about misleading guidance from the MR. And that would indeed be a valid concern, as shown on this slide here. If we revisit where we were before, we were saying that MLEM for low count data gives higher and higher noise. If we just do a quadratic penalized MAP-EM, then we over-smooth and we lose detail. If we start to use MR guidance in the form of Boucher, then the kind of thing that can happen here is that we end up with misguidance. So in other words, the smoothing here takes place across directions that the MR says are okay to smooth across, but they may not at all correspond with the structures in the original PET distribution. So we get this misguidance problem. So one could say that's where we got up to before deep learning. Obviously, there are many other variations on this, but this, I hope, is a reasonable summary. So that motivates us then to get into deep learning, because those conventional methods, either we're dealing with noisy data, giving rise to noisy images with MLEM, or we're compensating for noise with MAP-EM, regularization, but that regularization can often be too simple. For example, doing a quadratic total variation, relative difference prior. These are not very dramatic regularizers. They're rather simple, we could say. Or we go to the other extreme and start to impose MR information, and that MR guidance, as we've just seen, could be wrong. So those conventional methods are assuming we know the physics model, assuming we know the data noise distribution, and crucially, they are assuming we know how to regularize. In other words, we're claiming we know how images should appear based on that P of x related to that energy function that we've just been looking at. But the question is, do we really know all of those things reliably? And probably we don't, and so that's where deep learning can come in. We can use real data, paired examples in supervised learning to come up with more accurate models between the data and the images and also even better model the noise, although I think we're all pretty happy with the possible noise model. But crucially, the one that deep learning can really help us with, and that's where we've done most of our work, is on defining the so-called probability distribution of high-quality images, that P of X that we saw earlier. Okay, so deep learning can really help there. So to understand what that P of X would look like from a deep learning perspective, it's really important to understand the concept of manifolds. So I've shown a very simple example here of a manifold. Imagine we've got MR images over here, and if you could just imagine that only having 3 pixel values, then we'd have a 3-dimensional vector space with pixel value x1, x2, x3, and all the conceivable T1 weighted MR images would occupy a kind of manifold part of that vector space. Likewise, we could have natural images in the top right corner here. This is a picture of the Thames, and they would also occupy another manifold of that vector space. And of course then, high-quality PET images would occupy yet another manifold of that high-dimensional vector space. And now what we're saying is that any given point in that vector space, we can assign some probability P of that particular image X. And then if we've got a noisy PET image, then what we'd want to do is try and get that to sit somewhere on that high-quality manifold, but obviously whilst being consistent with the data. And what we'll be looking at in a moment then is trying to encourage images sitting on that manifold, looking at paired data where the image is actually associated with a sinogram or indeed without pairing to sinograms, and that's where the generative AI will come in. So quickly then, let's look at how MapEM would be morphed into FBSEMnet. All we're doing is taking exactly what you just saw before, except we're replacing that U of X expression, in other words, the direction that would take us in a direction to reduce that energy. We're just going to replace that with a simple CNN network. That's in essence what we've done. And this CNN network would be trained on an end-to-end basis where you'd put in low-quality data, and you would require that the output, using some loss function such as mean square error, you'd require that the output match a high-quality image. And so we do end-to-end supervised training of that CNN to encourage that unrolled iterative pipeline to deliver high-quality images thanks to our learned prior, effectively gradient of the prior, you could view that as. And then we'd still combine the directions as we did before in the previous MapEM example. So if you do that, these are the kind of results that you get. Borrowed this slide from George with modifications though. So we'd have the ground truth on the left here. This is data fidelity-based OSEM. And then if we do a MapEM regularization, this is not using any guidance, we might get a result like this. And then if we do the supervised deep learning approach, we would get results as shown on the right-hand side, which I hope you would agree are outperforming the OSEM and MapEM. And here we've not even included the MR information, but when we do include the MR information into that CNN, then we can get even better outcomes. And that's what I did with Abafaz. That's what he implemented some time back. If you want to see better results still for FBSEMnet, please do consult that original paper. Okay, so there's the bias variance kind of trade-off of comparing a conventional EM method with a MapEM method, and then the supervised unrolled deep learning method, where as we increase the trainable parameters, then we can get a notable improvement in image quality. In other words, heading towards lower noise and lower bias in our reconstructed images. So this is where we've got to now. We're saying conventional model-based methods could be characterized in this way here, where we're saying we're not doing any deep learning. We're making all of the assumptions about mathematics, physics, stats, and images. Generalization is great for all kinds of data. So that means the reconstruction challenge would work well for people that are using these kinds of approaches. So they don't need to worry necessarily about some kind of out-of-distribution data. And the trouble is, though, reconstruction quality, as we saw earlier, is going to be moderate because we've got those issues that we saw earlier. But then what we've done by using the deep learning approach, the Unrolled network, is that hopefully you've seen, just by those example images, we've gone from moderate image quality to good image quality. However, it's come at the possible loss of generalization capability. We could surprise the FBSEM net by some very unusual looking image, and we might end up with some errors or hallucinations, and so generalization is a concern. And also the unrolled deep learned methods like FBSEM net also need paired examples of low quality data with high quality references that they need to achieve. And it's very hard to come up with both high quality, both examples of images and data in pairs. That's not an easy task. And so in come then the generative AI methods, diffusion model-based methods, where we can see the differences are, as I'll go into presently, in fact next, we can now get away with just learning from images only, and we go from moderate to better levels of generalization, because we're no longer doing supervised learning for a very particular scanner, very particular noise level. We're now just instead learning the manifold of high quality images, just learning that P of X, although that's going to come at the loss of image quality, not always doing as well when we're within distribution for the unrolled deep learning methods. FBSEM net will always do better if you give it a test time example that corresponds to the training domain. And, but the other advantage of generative AI methods, though, even though the quality might not be as good as the unrolled methods, we don't need the training pairs, we just need a high quality example images, but we can also generate multiple samples sampling that posterior density and therefore have some notion of uncertainty or a credibility interval on our images. So I've now stolen a lot of slides from George. This was his title slide from his talk earlier, and he basically picked up the method of Imraj Singh. Chris and Simon were involved in that and took that a bit further. I'll just go over some of the basic principles then of using generative AI or diffusion models in particular in the context of PET image reconstruction to try and get some of those advantages that I just mentioned in that rightmost column. So you should all now be incredibly familiar with this kind of picture, where with diffusion models, what we're doing is taking some high quality image and then slowly degrading it by adding Gaussian noise until we completely lose the original information and end up with pure random Gaussian noise. And then what we're doing with the generative modeling is taking some random example of Gaussian noise, which is easy to do in Python. It's just one line of code, so anyone can generate something on the right-hand side. And then what we're going to do is train a network to slowly denoise that towards a sample from our high-quality manifold P of X. So we can look at that in the following way. So these are like different manifolds, if you like. We've got the Gaussian noise manifold on the right-hand side. This is just the manifold of all of those random images. And on the left-hand side, we've got our desired P of 0, thank you. And what we're going to do is just map from one to the other using effectively a method that is analogous to what we've been talking about before, a gradient of the log prior. And what we do, just to accelerate a bit here, is we approximate that necessary score vector that tells us the direction to go in to get to more likely images. We approximate that by using a deep network, which turns out to be very simple to train because it's just a denoising network, and nearly anybody that's done anything in deep learning knows how to train a denoising network. All you need to do is plug in the noise level as an input and be able to denoise at different levels. So I've given a very rapid description of how you do it. Maybe in the interests of time, I'll move on, but I did actually code something up like this myself over the summer, so if I can code it in PyTorch, I'm sure you can too. Just got to learn how to denoise. So let's take a look then at what's going on when we plug that kind of a model into image reconstruction. So here is our high quality manifold. This is like a prior probability density for just 2 pixel images, x1, x2, 2 pixel values, and we can see that we've got high probability for this combination of x1, x2, low probability in the middle, low probability around the edge. So that's our P of x in a 2D space. And then what that diffusion model is doing is taking some random seed, some random image, and then doing these generative denoising steps to effectively land us at a high probability image. And then what we're doing with data fidelity-based reconstruction, such as MLEM, is, as you know, maximizing the Poisson log likelihood. And what I've shown here are just these blue circles indicating constant values of Poisson log likelihood, where we're going to higher likelihood towards the middle of this example. So what would that look like? Here's a uniform starting estimate for MLEM, a uniform image, and then what we do is these data consistency steps, gradient ascent effectively of the Poisson log likelihood to arrive, although we've stopped, if we'd have gone into the middle there, you'd see that's low probability. That would be a very noisy maximum likelihood estimate, but we can see if we stop early in MLEM, we can get quite high quality images. So what we've done then, the work that George Weber has done based on the work of Imraj Singh, is to combine those two together for the context of PET image reconstructions. This would be image reconstruction by conditional diffusion sampling, because now we're doing the generative process, but interrupting it. So those green arrows are the generative steps of the diffusion model, but we're then interrupting it with data consistency, if you like, gradient ascent based on the Poisson log likelihood, shown by those blue arrows. That's going to head towards some kind of level of Poisson log likelihood that's also in agreement with, or rather for a given Poisson log likelihood level shown by those circles, we're then going to sample from the posterior at a fixed Poisson log likelihood. So that's what we have proposed here. We take a regular MLEM reconstruction and we look at the Poisson log likelihood as a function of iteration, and then effectively generate 100 time steps from that 1 to, for example, their 8 iterations. And what that translates to is the following. We start off with random noise. What we do first of all then is denoise that using our deep network. That's our denoiser that was very easy to train. So we get a denoised image, and then that denoised image, what we do effectively is use something like MLEM, basically gradient ascent of the Poisson log likelihood to get some target level as defined by conventional MLEM. Once we've reached that level, we then have if you like, a data conditioned denoised image. And then, of course, we need to get back into that generative pipeline. So we renoise it to get to this corresponding time step, and then we can go around again. We can denoise, improve consistency with the data, and then renoise to enter back in. And so we're just toing and froing between the Poisson log likelihood and the generative model. So if you do that, you get the results shown on the right-hand side here. This is our Poisson likelihood scheduled approach, where we're not choosing anywhere near as many hyperparameters as had been proposed by the method of Imraj Singh et al. So you can see here we're doing comparably well, but the key here on the right-hand side is very limited number of hyperparameters, and instead we're just choosing our level of Poisson log likelihood and then taking samples of the posterior for that fixed level of Poisson log likelihood. So maybe I could have shown there that there are possible issues, though, with this reconstruction. I think I'm running out of time. Chair is showing me 1 minute, I think, now. But you can see that we do have possible hallucinations here compared to the other methods. Although if I look at OSEM, I can see there's a gap there. It shouldn't be there in the ground truth. And we're seeing this kind of gap there as well that could be a possible hallucination. And bias variance trade-off just shows us that these methods kind of sit nicely down here, beating the model-based methods, but not doing quite as well as the high number of trainable parameters in FBSEM net. Okay, those are example reconstructions very rapidly. This is the 10% MLEM reconstruction. You can see it's very noisy. If we go to our method here, then you get a bit more detail. I'm afraid the slide, the screen doesn't do justice to this, but you can see we've got a bit more detail compared to the 10% MLEM, and also compared to Imraj Singh's method, we're not suffering from some of those artifacts that he saw by using the relative difference prior between transverse slices. But just to quickly finish, if the chairs will allow me, these score-based generative models are quite general in the sense that it depends what high-quality images we use to train our diffusion model. So there we were just using full-count OSEM images. But we could do more exciting things, such as superimpose multiple subject data together to get higher signal-to-noise ratio images in order to learn the manifold of even higher quality PET data. So George Weber had presented that as a poster here. I'm sure you can search out that contribution on IEEE Explore, at least the abstract will be available. Okay, do I have 30 seconds to talk about ultra-fast reconstruction? I'll just wrap up here. This is what our entry would have been in this rapid image reconstruction challenge had we entered. So this is work by Mavindu, another PhD student in the same year as George Webber. And what we did here was take a method I'd put forward quite a few years back now, an incredibly simple method which said take a sinogram, learn some network to do something to that sinogram. We know it's going to be something like ramp filtering. Do something to the sinogram such that when you back project it and then forward project it, make sure that the forward projection of our reconstruction agrees in this self-supervised way with what we started with. So that was the very simple 2D construct. Mavindu's done a heroic job of turning that methodology into a functioning, fully 3D methodology where he came up with this approach of taking the data, reordering it, and then putting it through this rather large UNet in order to do that kind of filtering process, reorder it back to the standard format, put it into Georg Schramm's parallel proj, back projector, get the image, and then parallel proj forward project, and then you do a loss between those two, and round you go. So we pre-trained on lots of example data sets to do that, and then once we pre-trained it, we just froze the network and then used it, and we got surprisingly good results, even though I feel like we could have far more enriched the training set than what we had done here. So we got results for this deep learned filter back projection for Poisson log likelihood and the relative difference prior that actually compare very well with MapEM, but all we had to do was a UNet and a back project and we're done. So had a word with Casper at some point, and apparently we could have stood a very good chance if our image quality was good enough of maybe being the fastest, but who knows? We didn't enter, so we don't know yet. Right, and also to say, if we look at bias variance trade-off for that method, then the reference MapEM would be that purple line, and the deep learned method would be that those red squares. This is looking at the, if you like, clinically relevant post-smoothing level shown here, and you can see that we're incredibly competitive when you start considering the practically used level of spatial resolution. So thank you to the chairs for allowing me an extra few minutes. Happy to take any questions if there is more time.